Hi everyone, this is Mrs. Musoff here. We're going to continue talking about limits today by specifically talking about limits that involve infinity. And basically, limits involving infinity are going to have to do with asymptotes for the most part. So vertical asymptotes and horizontal or end behavior asymptotes. All right. One type of limit involving infinity is when the answer to the limit is positive or negative infinity. And that would imply that there is a vertical asymptote going on. So another definition of a vertical asymptote is x equals a is a vertical asymptote if the limit as x approaches a, right, from the right of the function is equal to positive or negative infinity, or the limit as x approaches a from the left of the function is equal to positive or negative infinity. All right, so if you know on your graph that the limit as you approach a number from either the left or the right is approaching negative or positive infinity, then that means there's a vertical asymptote there. All right, and once again, that the two-sided limit of a function does not exist if the left side and the right side are not equal. Okay, so in this first example, we're just kind of analyzing that vertical asymptote of the function to identify some of those limits. So for example, f of x equals 1 over x plus 2. What we would want to be able to do is graph this without a calculator so that we can analyze that vertical asymptote. All right, remember vertical asymptotes come from the denominator. That's how I know it's x equals negative 2. And since that vertical asymptote is odd, we know the branches are in diagonal corners. All right, but you could also plot points to figure that out. So, based on this graph that I've drawn, I can see that the limit as x approaches negative 2 from the left, and that's me where I'm drawing my pencil right now, is going down, 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 so it's equal to negative infinity. The limit as x approaches negative 2 from the right, that's this part, it's going up, 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 so that would equal positive infinity. And these three dots just means therefore. So therefore, the limit as x approaches negative 2, no plus or minus, so that means we're talking about the two-sided limit, does not exist because those one-sided limits aren't equal. All right, so again, if the answer to a limit is negative or positive infinity, that means there's a vertical asymptote most likely at that piece, or at that number. Okay, same kind of thing in this next example. This one should look a little familiar because it was on one of our homework assignments. The limit as x approaches 0 of 1 divided by x squared. Again, based on that denominator, we know there's a vertical asymptote at x equals 0. But since it's even, that means the two branches are right next to each other. And so if I were to find the limit as x approaches 0 from the left, that would be this piece right here. It's going up, 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 up forever. So that'd be positive infinity. And the limit as x approaches 0 from the right, up, 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 is also positive infinity. And since those are the same, we can say, therefore, the limit as x approaches 0 is equal to positive infinity. All right. On the homework problem, it asked why you can't use substitution to evaluate this limit. And I'm sure most of us recognize that if we substitute 0 in, you would get 1 divided by 0, which is undefined. But notice how there is still a limit, and that means that it is important that even if you get undefined, you still graph it because sometimes that limit still exists. All right, the other type of limit involving infinity is when we're talking about the limit as x approaches positive or negative infinity, and that would be basically the end behavior of your function, which is typically defined by horizontal or end behavior asymptotes. Or not typically, but sometimes can be. All right, so y equals b is a horizontal asymptote if the limit as x approaches positive or negative infinity of the function is equal to b. All right, and remember, always with rational functions, we can identify the horizontal or end behavior asymptotes by figuring out if they're top-heavy, bottom-heavy, or the same. And that's referencing the degree in the top and the degree in the bottom, so the highest exponent. All right, so in this first example, the limit as x approaches negative infinity of 1 divided by x plus 2. If I wanted to calculate that limit, I can't really plug in negative infinity because it's not a real number, right? You could, if you wanted to, plug in like values for x that are approaching negative infinity. So I could plug in like negative 10 and then negative 100 and then negative 1,000, right? And kind of notice a pattern in order to figure out that limit. But probably the faster way to do it is just to graph it. This function, I know, has a vertical asymptote at negative 2 and a horizontal asymptote at 0 because it's bottom heavy. And so this is the graph I can end up with. So if I want to know the limit as x approaches negative infinity, that would be right here. And as I approach negative infinity, I'm approaching that horizontal asymptote, which was 0. And that's why my answer would be 0. All right, same kind of thing in that second example, the limit as x approaches infinity of 1 divided by x plus 7 minus 5. Again, I would find my vertical and horizontal asymptotes. Keep in mind, I know some people, like on the graphing review, maybe thought they had to combine these together to find the graphing information. But this is really just a transformation of our parent function. Right? The function 1 over x, you could think of it as 1 over x minus h plus k. So the bottom number is your left-right shift, and the number at the end is your up-down shift. And so that's how I could figure out the vertical and horizontal asymptote also. Because I know this normally has a vertical and horizontal asymptote at 0, but if I shift it left 7, like this is doing right here, that would change my vertical asymptote, and if I shift it down 5, that would change my horizontal. Okay? But no matter how you decide to graph it, at the end of the day, as long as you get this graph, that's what matters. Because then as x approaches infinity, that's this part of the graph here, it's approaching that horizontal asymptote, so as long as you could identify the horizontal asymptote as negative 5, you can calculate your limit. All right, so a lot of the limits involving infinity have to do with understanding asymptotes. So if that's still something you struggle with, this is a good chance to practice. Okay, on the back page, we kind of continue with that, just another format of it, and that's the end behavior model. All right, so for large values of x, we can model the end behavior of a more complex function using a simpler one. All right, so when it says find the end behavior model, the idea is you want to write an equation. So model is just another word for equation. All right, so you want to write an equation or a function that has the same end behavior as the given function. And typically that means you need to find your horizontal or end behavior asymptote and make sure they match. So in this function, I have 1 divided by x plus 2, which is kind of like saying left 2. So I know my end behavior asymptote, since this is bottom heavy, is going to be y equals 0. All right, so I'm trying to think of a simpler function that I know is very similar to this one that also has that same end behavior asymptote. Well, remember, this is the same thing as the parent function 1 over x, just shifted left 2. The left 2 didn't change the horizontal asymptote, so I can just use the parent function to represent my end behavior. So that's why my end behavior model is just y equals 1 over x. All right, same kind of thing in letter B. This is a more complicated function, but if I can recognize what terms in this function are actually contributing to my end behavior, I can just focus on those. So for example, this, if I wanted to find the end behavior asymptote, this is top heavy because the degree in the top is 5 and the degree in the bottom is 2. Well, when it's top heavy, the main thing that's going to contribute to your asymptote are those leading terms. So the 2x to the 5th on top and the 3x squared on bottom. And if I divide those, I end up with 2/3 x cubed, and that is actually going to be approximately the asymptote at the end. So that's the function that I would use to model my end behavior. All right, and the idea of an end behavior model is it should help us evaluate limits that are approaching infinity. So for example, this is similar to that last one, but now we're actually calculating the limit. So we want to find the limit as x approaches infinity of this function. Well, again, that would be the end behavior. All right, so this, as x approaches infinity, that will always tell you to use the end behavior. So I'll look at this function and I'll say, oh, degree on top is 3, degree on bottom is 3. Since they're the same, that means I just divide the coefficients, and that would be my end behavior asymptote. Well, if that's my end behavior asymptote, then that means as x approaches infinity, y should be approaching this value, so that would be my answer. All right, so a lot of these you are going to maybe want to draw some rough sketches, or at least make sure you're confident with your horizontal or end behavior asymptote. Okay, down at the bottom are just some extra notes that might come up when you're practicing the homework. That one function we've talked about before, sine x over x, just a reminder about what that graph should look like. In the past, you've seen problems that ask for the limit as x approaches 0, so that would be this point right here. But now you're going to see we're looking for the limit as x approaches the infinities. That would be the end of our graph, and notice how that's where the wave starts to really get smaller and smaller, and it basically kind of hugs the x-axis, which would mean it's approaching 0. All right, so again, just 2 limits we want to be really familiar with. Some other side notes that might come up. Remember this function here, this was on the graphing practice, right? This represents the greatest integer less than or equal to x. All right, so just remind yourself that's like that step graph. It looks something like this. All right, going in both directions. So just kind of pay attention to what's happening in this graph. Just make sure you're familiar with it, I suppose. And then something else that sometimes comes up is just making sure we know how to factor sum and difference of cubes. All right, this is an example of it. The technical formula would be like a minus b, and then a squared plus ab plus b squared. Feel free to look that up, all right, but just something that shows up on occasion, so it's good to be familiar with it. Okay. The last little thing I wanted to mention is that sometimes you will have functions, for example, this right here, where you want to find the limit at an actual value. So as x approaches 1. And perhaps you say, oh, well, I don't really know what this graph looks like, so let me at least try plugging it in. And when you plug it in, you notice how you would get 0 in the denominator. Right? And so then plugging it in won't work. So if plugging it in doesn't work, that means there's either, a whole or a vertical asymptote, but either way we need to be able to factor these. Now the top we should know how to factor because that's a quadratic. You can do guess and check, which is the method I use, or you can do split the middle, whichever works for you. Some of my students do slide and divide. Whatever works, but this is something we should be able to factor. Right, 2x plus 5x minus 1. The denominator, on the other hand, since it's a cubic, we would have to factor it by grouping, and grouping won't work here. So since you know how to factor the top and you see that an x minus 1 comes out, we would just use that x minus 1 to synthetically divide, which would help us factor. And so that's the work you see over here, right? I say, oh, well, I know x minus 1 is a factor. Let me divide by that x minus 1. Whatever I'm left with, turn that back into a polynomial, and now I can cancel out the whole and use regular substitution. Okay, so just some little extra notes that might help you with some of those practice problems. All right, that's all for today. If you have other questions, just make sure you write them down and ask your teacher when you get a chance. Thanks for tuning in.